Hello, I'm Andy Anderson, and today I'd like to briefly introduce you to the educational research that's the foundation for the development of carbon time units, research on a learning progression for carbon transforming processes. If you look at the goals for carbon time units, all 5 units have similar kinds of goals. They focus on 5 processes at multiple scales: combustion, photosynthesis, cellular respiration, biosynthesis, and digestion. Every unit has inquiry goals that Jenny will talk about in the next presentation, and application goals that I'm going to talk about now. For each process, we hope that students will learn the answers to 3 questions. To the movement question, we want them to be able to trace movements, the physical movements of atoms through systems and processes. The carbon question, we want them to be able to trace carbon and other atoms through chemical changes involving rearranging into new molecules. And the energy question, we want them to be able to trace energy through carbon transforming processes. These connect with a key part of the next generation science standards called cross-cutting concepts. There are 7 cross-cutting concepts, and in particular, we want to draw attention to one of them: energy and matter, flows, cycles, and conservation. So why is this so important? Why do we single out matter and energy as uniquely important concepts? The reason is that matter and energy conservation make it possible to trace matter and energy at different scales, from subatomic to universal, through all kinds of systems: physical systems, living systems, earth systems, technological systems, and while engaging in many scientific practices such as explaining, predicting, modeling, designing, and investigating. So today, I want to discuss 2 main topics. First, our goal, what it means to use energy and matter as a cross-cutting concept. And second, how students can achieve the goal. What we've learned about learning progressions, which are how students' ideas about matter and energy can develop over time. So, first of those goals, I want to make 3 points about what it means for students to be able to trace matter and energy through processes. First, they need to understand conservation laws as rules, not just facts. Second, they need to understand matter and energy in a hierarchy of systems at different scales. And third, I want to talk about some of the key things that make it hard for students to do this. So, the idea that conservation laws are rules and not just facts. If you think about something like this sentence here, you probably haven't thought about verb, noun, agreement for many, many years, and yet instantly you can see that there's something wrong with this sentence. Here, 16 years old. You know instantly a rule has been broken, and so this is not a correct English sentence. So that's how rules work. They're often working in the subconscious, and you become aware of them when you see them broken. So for a biologist, if you sees a sentence like this: breathing converts CO2 to O2, we'll instantly see there's something wrong with this sentence too. A biologist might give a detailed explanation of how CO2 actually comes from cellular respiration and the carbon originally comes from food. But any scientifically literate person, even someone who studies physics and knows nothing in particular about physiology, would see that the process is impossible. It doesn't answer the question, where did the carbon come from? So the second idea, matter and energy are traceable in a hierarchy of systems. This hierarchy goes from very, very small to very, very large. Carbon time focuses on systems somewhere in the middle. The smallest systems are atomic molecular systems, where atoms are recombined into new molecules, and the largest system is the Earth itself. Let's take an example. So here is a simple food chain in which grasshoppers and earthworms are eating organic matter from plants, and robins are eating the grasshoppers and earthworms. This is the macroscopic scale. At the atomic molecular scale, it's possible to talk about changes in atoms and molecules, such as photosynthesis, where carbon dioxide and water combine to make glucose and oxygen, or cellular respiration that does just the opposite. At the large scale, at the ecosystem scale, we can see this food chain as part of a more general carbon cycle. We can say that the general pattern here is that matter cycles, energy flows, and the key processes that I talked about before, photosynthesis and cellular respiration. One converts matter from inorganic to organic form, the other from organic back to inorganic form. So let's think about how you might apply these into everyday situations. This leads to a discussion of why these are hard for kids. So here are 5 true-false questions. You might want to pause the video for a minute now, read the questions, and think about your own answers to whether each of these statements is true or false. So here are the answers that we would hope students would learn to give as a result of carbon time. Some of the wood is converted to heat and light energy when the match burns. This is false. Matter is not converted to energy in chemical or physical changes. The materials or substances that make up the wood or match are destroyed when it burns. This is true. It's no longer wood, now it's something else. The molecules of the wood are destroyed when it burns. This is also true. The molecules of cellulose and lignin have been broken up. They cease to exist. The atoms of the wood are destroyed when it burns. This is false. All the atoms are still there, just in different molecules. The matter of the wood is destroyed when it burns. This is also false. All of the matter is still there. It's just now in carbon dioxide and water and other substances rather than the wood itself. So, what makes these ideas difficult for kids? 2 key ideas. A lot of kids think matter-energy conversion is possible, and students often have difficulty using matter and scale words correctly. The first of these ideas, matter-energy conversion. We believe that classical physics is an essential foundation for understanding relativistic physics for all students, but most students have learned about E equals mc squared and tend to use it as a convenient fudge factor. So many students agree with each of the statements here. They would say the burning match loses mass because some of its mass is converted to energy. Exercise helps us lose weight by burning off fat as energy. Cellular respiration converts glucose to ATP. Gasoline is converted to the kinetic energy of a moving car. Now in each case, tracing matter is difficult because there are gaseous products, and therefore the visible products weigh a lot less than the visible reactants. And that causes students to invoke matter and energy conversion, but it's really a fudge factor. You know, they're actually just not accounting for the gases that are involved. The other difficulty that we see students having has to do with using matter and scale words correctly. The question of what's conserved is actually pretty complicated. In physical changes, like changes of state, volume is not conserved. Something can be bigger or smaller, and you don't ask where did the volume come from or where did the volume go. But mass, matter, substances, molecules, and atoms are all conserved. So every molecule of water, for example, that's there when water is a liquid is still there after the water evaporates. Chemical changes are different. In chemical changes, volume is still not conserved. Substances are not conserved. In photosynthesis, for example, the water is no longer there at the end, and molecules are not conserved. But on the other hand, atoms and matter and mass still are conserved in all physical and chemical changes. So this is hard stuff. Our attempt to understand how it is that kids can understand this over time is the focus of our learning progression work. So there are 2 things I want to talk about with respect to learning progressions. First, I want to give you a brief overview of what learning progressions are. And then I want to talk about how discourse and knowledge and practice, 3 different dimensions of learning progressions, look different for students at elementary and middle and high school levels, or what we would call levels 1 through 4 in the learning progression. So here's some definitions. A learning progression is a description of increasingly sophisticated ways that students have of reasoning about a topic. The learning progression includes a framework and assessment tools and teaching strategies. In this presentation, I'm going to talk just about the framework. There will be other sessions in the professional development where you learn about the assessment tools and teaching strategies. So, what progresses in a learning progression? We think about 3 dimensions: discourse, how we use language to describe and explain the world; practices, scientific practices, and their precursors and less scientific practices; and knowledge. In next generation science standards, this is described as cross-cutting concepts like matter and energy and disciplinary core ideas. So practices and knowledge are probably pretty familiar to you, but we expect that discourse may be a new idea. So the core idea we're working on here is that learning science is like learning a second language. Everybody, when they learn their first language, English or Chinese or French or whatever, has to master what we call everyday discourse or forced dynamic discourse. And it turns out that that's really quite different from scientific discourse. So learning science can be very much like learning a second language. And this second language is powerful for analyzing the material world. And we often have the illusion of communication because speakers of everyday discourse and speakers of scientific discourse use a lot of the same words like energy and matter and weight and material and so forth. But they have subtly but really importantly different meanings. So let me illustrate that. That we live in Michigan, and so I'm going to use an example of a food chain here in Michigan. Black medic is a common clover-related weed that grows here. Rabbits like it, and so rabbits eat the black medic. There are coyotes that sometimes eat the rabbits. Sometimes the coyotes die and decompose. So how would kids at different learning progressions tell the story of this food chain? Let's start with the lowest level, level 1. And level 1 is mostly typical of elementary school students, so we don't use it very much in our descriptions of our learning progressions for middle and high school students. But for level 1 students, this is a story about actors, the rabbit and the coyote, and the things that they need to achieve their purposes in life, like living and growing. So food is necessary for growth, but that's not to say the same thing as food is what what animals are made of. That for level 1 students, food enables growth. It's not the materials for growth, so you are not what you eat. And water and air are also necessary for growth. The plant is there mostly for the rabbit to eat, but it has a purpose in life too, which is to grow. And their explanations focus on why plants and animals act as they do, not on tracing matter and energy. So we can think of level 1 accounts as having a structure something like this. They're actors, like people and animals and plants and flames. And those actors have purposes like growth or gaining or losing weight or making things burn. And in order for them to achieve their purposes, they need enablers like food and sunlight and care or a match or things like that. Level 2. Level 2 students start to become somewhat aware of cycles, but in a very different way from the carbon cycle that I was showing a few minutes ago. For level 2, the story is still mostly a story about actors and their actions. And the cycles they're aware of tend to be sequences of events. They're not really tracing matter and energy. And energy in particular is something that causes events to happen, such as life. So for level 2 students, there are often 2 kinds of cycles. One kind of cycle we call the nutrient cycle, in which plants use sunlight and nutrient from the soil in order to grow. People and animals use plants in order to grow. Decay happens when they die, and that supplies more nutrients to the soil so the plants can grow again. And then completely separately, there's the oxygen-carbon dioxide cycle, in which plants give rise to breathe out oxygen, which people can breathe in, and they breathe out carbon dioxide, which plants breathe in. And in both of these, it's notable that the plants are there mostly to help the people. So how about level 3? Level 3 is typical of a lot of students at the end of courses in high school and even college. These students learn lots of ideas, lots of facts about organisms and cells and molecules. But the trouble is those facts are not always correct. And they learn lots of facts about different scales, such as macroscopic and microscopic and atomic molecular, but they're often mixed up and unconnected. And for them, matter and energy conservation are facts rather than rules, so they don't apply them consistently. They see large-scale connections, and they see that food chains involve flows of matter and energy, for example, but for them, they still see this as two different cycles, that there's still a separate nutrient and oxygen-carbon dioxide cycle. Then finally, level 4. This is the level that we're aiming for. At this point, the students are able to trace matter and energy across scales. So at the atomic molecular scale, they see the rabbit and the coyote and the medic and the decomposers are all systems that chemically transform matter and energy. They see that matter and energy endure while systems are temporary, which is very different from the level 1 students. For the level 1 students, the enablers such as food exist temporarily, while the things that endure are the rabbit and the coyote and the plants. And they fully recognize the role of gases in matter cycles, and they fully recognize chemical energy as a key kind of energy. So they make large-scale connections through the carbon cycle, in which matter cycles and energy flows. And we're back to our large-scale carbon cycle diagram. So you'll see matter cycling into and out of the atmosphere, and energy flowing from sunlight to chemical energy, and finally to heat and work. So that's the overall story of our learning progression. One final note I'll make is that learning progressions involve understanding at different scales, that levels 1 and 2 are mostly macroscopic, with some notion of large-scale cycling, but more sequences of events than in tracing matter and energy. Level 3 is aware of all the different scales, but not able to connect them very well. And only at level 4 do we see students reliably making connections across scales from the atomic molecular up to the ecosystem and global scale. So, coming back to our goals for the carbon time units, I hope this has helped you understand the goals in a deeper way. You'll be learning about the strategies and materials we have to help students achieve those goals in the remaining parts of the professional development. One last thing. For a musical summary of this presentation, check out the biosynthesis song in the files for this professional development. Thanks and goodbye.